Okay. Hello, good morning to everybody. Today we shall start discussing physical process models. So the type of modeling we will apply when we would like to describe physical processes. We have two main categories or two main groups of models. First one is adsorptions models that goes together with ecotoxicological models. So you may recall that here we are going to model the transfer between the four ecospheres. Then the next topic would be that of transport, balance, and chemical reaction models. That would be the subject of next week. Um, how do we include ecotoxicological processes in our models of ecosystems? We have said last Monday, that toxic substances are found in several forms in the different ecospheres. We said that we may introduce four different spheres or ecospheres: the lithosphere, the hydrosphere, the atmosphere, and the biosphere. We said that spheres can be in equilibrium with each other, or most probably, we may describe situation of dynamic phenomena of exchange of substances. On Monday, we have seen already the first example of a model describing the exchanges between the atmosphere and the hydrosphere. We said that the key model employed for describing these flows is the Henry Law model, the model based on the Henry laws. And we said that the Henry law constants are numbers or figures or constants that describe characteristics of the different toxic substances. Today we will deal mainly with exchanges with the biosphere. First of all, it is useful to recall some definitions. We talk about bioaccumulation when we describe the fact that biological systems or ecological systems or living objects tend to accumulate toxic substances by accumulating them from matrices like air, water, soil, and food. In particular, we talk of bioconcentration when we describe the bioaccumulation of toxic substances from water into biota, so from the hydrosphere into the biosphere, while we talk about biomagnification when we describe the bioaccumulation of substances through transfers in food webs. So biomagnification is much a process related to internal transfer of toxicants in the biosphere through food webs. First of all, we shall introduce models employed for describing the equilibrium between the lithosphere and the hydrosphere. I recall you that last Monday we described interaction between hydrosphere and atmosphere. Now we talk about interaction between lithosphere and hydrosphere. So what is passing from the water matrices or from the water matrix into the solid or lithosphere. For describing this kind of processes, we employ three classical models that are called isotherm models: the Redrick-Peterson, the Freundlich, and the Landwehr isotherm. These are isothermal processes, meaning that for simplifying, for the sake of simplification, we assume that these exchanges take place in condition of constant temperature, so no changes in the temperature. Or if you want, we assume a constant temperature, and then we try to describe by mathematical modeling the flow taking place at constant temperature between lithosphere and hydrosphere. So we seek identifying the equilibrium situations for these exchanges. And finally, we shall introduce the more general model that is called the partition coefficient model, in which we introduce a methodology for finding equilibrium between the different spheres, in particular here lithosphere and hydrosphere, by employing the approach of partition coefficients. In practice, you may realize that when we are talking about lithosphere and hydrosphere equilibrium, we are thinking about a process of adsorption that you already have seen in several other conditions or in several other classes. Now we shall discuss how we may deduce the mathematical model for describing the process of adsorption. We may say that contaminants and pollutants, like for example pesticides, heavy metals, and so on, but also nutrients, are found mainly in the sediments of aquatic ecosystem or in suspended matter. So you, as an environmental engineer, you already know that when you are looking for the fate of some toxic substances, you should look to the fate of suspended matter. Then we are seeking to find the condition for an equilibrium, that it is a dynamic equilibrium that is achieved very quickly, meaning that there is an equilibrium between the process of adsorption, so sticking of dissolved substances in the water column onto solid, so particulate. This is passing of substances from dissolved forms in the water column onto solid phase, so onto particulate. These are typically called surface processes, and we say that these surface processes reach very quickly an equilibrium that may bring the process in a steady state condition. What do we mean by steady state equilibrium? We have already discussed the various types of equilibrium. A steady state equilibrium is an equilibrium in which there is a balance between a transfer in one direction, for example, from the hydrosphere, so dissolved substances, into the lithosphere, particulate, and there is contemporarily a condition of equilibrium of a flow of exchange between the suspended solids and the dissolved forms of these contaminants. So the steady state is reached when we have the same quantity or the same matter that is being absorbed from the dissolved quota to the solid phase, and the same matter that is desorbed from the solid or particulate phase onto the dissolved phase. We said that we model this kind of processes using isotherms, and the isotherms depends, or if you want, the parameters describing these isotherms processes depends on the substances involved. The substances involved, in particular, the process of adsorption, are the adsorbate, so the substance that is transferred from the dissolved phase onto the solid, onto the particulate, and the adsorbent. The adsorbent is the particulate that adsorbs the substance from the dissolved phase. So when we describe these models, we shall consider that we will have to include parameters that characterize both the substance that is being transferred from the dissolved phase onto the solid phase, so the adsorbate, but also we have to characterize the substances on which these contaminants are adsorbed, so the adsorbent. As I said already, this is a surface process, so we may say that the solid surface is what mainly involved. By surface process, we mean that the dissolved substance in the liquid phase is transferred onto the surface of the solid phase or the particulate, and more specifically, the adsorbate is transferred from the dissolved phase in the liquid onto the surface of the adsorbent in the solid phase. A very general model we may employ for describing this process is that described by this equation, in which we say that the adsorbed fraction, so the solid concentration of a contaminant or a pollutant, is equal to an equilibrium constant K multiplied for the concentration in the water, so the liquid concentration, divided by a dimensionless generalization constant delta, plus another constant H that is related to the heat of adsorption, times the concentration in the liquid phase Cs elevated to a dimensionless heterogeneity factor beta that describes somehow the characteristics of the adsorbent. So here we have 4 parameters: the equilibrium constant H and the the equilibrium constant K and the parameter that is related to the heat of adsorption, or if you want, it is related to energy released by the molecule, but it is sticked, transferred from the liquid phase onto the solid phase. H, and this constant is related to a heat of adsorption, so the energy released in the process of adhering from the dissolved phase onto the solid phase. Then there is another parameter beta that tries to take into account the heterogeneity of the adsorbent, and another parameter delta that is a generalization constant. From this very general model, we may discuss particular cases that describe the process of adsorption. The first case is that of the generalization constant delta equal to 1, and this is called the Redlich-Peterson isotherm, in which we have that the concentration in the liquid phase is equal to equilibrium constant K times the concentration in, the concentration in the solid phase QS is equal to the equilibrium constant K times the concentration in the liquid phase divided by 1 plus H time H multiply the concentration in the liquid phase elevated to a power beta that is linked to the heterogeneity of the adsorbent. I anticipate that the parameter beta is the one that accounts for multi-layer adsorption, and we will see soon what we mean by this. Another case that may be derived from the general model of the general isotherm model that we have introduced is that what is called the Langmuir isotherm. Langmuir isotherm assumes an homogeneous adsorbent surface, so the exponent beta is posed equal to 1, and a monolayer with a capacity K over 8. So a monolayer, the Langmuir isotherms describes An homogeneous adsorbent surface. Homogeneous means that the surface of a particulate, of a particle that absorb the dissolved molecule is homogeneous, equal in space, in all the directions, in three directions of space. But moreover, the Langmuir isotherms assumes a monolayer adsorption process. Monolayer means that the particle, solid particle that is absorbing the dissolved fraction of a contaminant is not infinite. Instead, it has a limited surface. And when the surface is totally covered, the surface of a particle is totally covered by adsorbate, then the adsorbent stops adsorbing. So the adsorbent stops attracting molecules from the liquid phase onto the solid phase. In this case, we assume delta and beta equal to 1, and the very simplified version of the general isotherm is the one expressed here. So the concentration in the liquid phase, in the solid phase, Qs, is equal to equilibrium constant K times the concentration in the liquid phase Cs divided by 1 plus H times Cs. In particular, in this condition, we may introduce another parameter that is K over H, that is called the capacity, the monolayer absorption capacity. So K over H is a parameter linked to the ability of the particulate to be covered by adsorbate. So the capacity of the particle, absorbing particle, of being covered by the dissolved contaminants. By experimental analysis, the environmental engineers may find useful these kinds of plots. Here we are plotting the ratio C over S. So the ratio concentration in the liquid phase divided by concentration on the solid phase. Sorry, this S is QS if you want, as a function of the concentration in the liquid phase. We see that depending on the different typology of adsorbent, clay loam, or loamy sand, we have different behaviors, but in general, we have some kind of linear relationships that links the concentration in the liquid phase with the ratio between the concentration in the liquid phase and the concentration in the solid phase. You understand that, for example, let me see if I can make my terrible drawings. If you assume, oh, sorry, one moment. Okay. Let's assume a constant concentration in the liquid phase. Then, given a constant concentration in the liquid phase, for example, here around 20 milligrams per liter, you see that depending on the type of adsorbate, the type of the adsorbent particle, being with that clay loam, or loamy sand, we have a different quantities of different quantities of contaminant transferred to the solid phase. In particular, let's see if I'm able to make it. Okay. Given a fixed concentration in the liquid phase, you will have, depending on the type of the adsorbent, you will have a higher or lower concentration in the solid phase. In particular, being C over S, so concentration in the liquid over concentration in the solid phase. So if this quantity grows, this means that concentration in the solid phase decreases. This means that clay is a stronger absorber than loamy sand. So loam is a stronger absorber or adsorbent than clay. This means that given the specific conditions of a liquid, of a water body, of a water environment in terms of concentration of a contaminant, depending on the type of a suspended solid, you will have different quantities of matter that is transferred from the liquid phase onto the solid phase. This type of consideration are obtained, sorry, let's see if I'm able, are obtained from the Langmuir isotherm, in which we put delta and beta equal to 1. So monolayer adsorption on homogeneous adsorbent surface. In this case, you may, with some simple algebraic manipulation, you may simply divide this by CS. When you invert this relationship, so you make CS over QS is equal to 1 plus H divided K to CS. And then you obtain, if you make a variable change, so you change the epsilon variable to CS over QS, you obtain a linear model. So we have a linear relationship linking the ratio between the concentration on the solid surface and concentration divided by the concentration in the liquid is equal linearly to H over K times the concentration in the liquid surface. And this is why H over K is called the monolayer absorption capacity of this particular adsorbent. So you see that from these empirical relationships, you see that the different types of adsorbent, clay, clay loam, loam, or loamy sand, have different adsorption capacity. In particular, the greater adsorption capacity are those that characterize clay particulate or clay solids. So if you have a water body with a dissolved concentration of contaminant, and in the water body also you have some particles of solids, suspended particles of solids, and depending on the characteristics of these suspended particles, being then clay, loam, or sand, you will have different adsorption capacities. So you start understanding here, but beside the characteristics of the adsorbate, of the contaminant, also the characteristics of the adsorbent or the suspended particles are relevant in describing or in building the model describing this process. Finally, we have a last example of adsorption isotherm, but it's called the Freundlich isotherm. The Freundlich isotherm, it is assumed an heterogeneous adsorbent with sorption sites that are energetically non-equivalent. So there is a kind of heterogeneity in the surface, the adsorbent surface. And in this case, we simply assume that the generalization factor delta is equal to 0 instead of 1. I recall you that in the preceding isotherms. Sorry. In the Langmuir isotherms, delta and beta were assumed to be 1. In the Freundlich isotherm, delta is assumed to be 0, and beta instead, or the exponent of the concentration in the liquid phase, is assumed to be 1 minus beta. This is the so-called Freundlich isotherms. You see that this has a log-log linear. This is a log-log linear relationship. If you take the logarithm of the two concentrations, then you will end up with a linear relationship. That explains in particular why in some cases you have these kind of relationships. As always, K over H is called the layer capacity, or the constant A that appears in front of the concentration in the liquid phase. We may plot these three isotherms. So you see that the Redlich-Peterson isotherm is a continuously, constantly growing isotherm. So you have that as a function of the concentration in the liquid phase, you have a constant increase in the solid phase QS, and the increase is, if you want, is the concentration on the solid phase increases at a constant speed. Sorry, one moment. While in the case of the Freundlich isotherm, you have still a continuous growth of the concentration of the solid phase, but is, however, slowly when the Redlich-Peterson. I recall you that the Freundlich isotherm, sorry, the Redlich-Peterson isotherm assumes sorry, the Langmuir isotherm assumes a monolayer homogeneous adsorbent surface. So what you may describe with these three isothermal models are a process of transfer from the liquid phase onto the solid phase that is constantly increasing in a Redlich-Peterson model, or it is constantly but more slowly increasing in the Freundlich isotherms, and then you have a Langmuir isotherm in which we have assumed a monolayer adsorbent capacity, so that the concentration on the solid phase reaches a kind of plateau. So the equilibrium is a dynamic steady state in which you have a constant absorption desorption processes that maintains constant the concentration of the solid phase. I recall you that all these models, these three models, are obtained in isothermal conditions, so that you may ask yourself what happens if the temperature changes. Let's say that we obtain this curve when we have a temperature T1. Let's see if I can draw. In temperature T1, you will have this kind of isotherms. Now we may ask ourselves, what happens if the temperature changes to a different value, a value T2, but is bigger than T1? So we are asking ourselves, what happens if the temperature of the system increases? T2 greater than T1. There are several ways of answering to these questions. In particular, you may recall that if the temperature increases, the concentration of the solid phase tends to decrease, so that if the temperature increases, you may imagine that all these curves tend to move downward. So in the case that the temperature increases from T1 to T2, where T2 is larger than T1, then all these curves tend to get lower. This means that at an equal concentration or a given concentration of a contaminant in the liquid phase, CS, then you will have lowering concentration in the solid phase QS. As a rule of thumb, you may remember this by thinking at catalyzers. You know that catalyzers are filters that tend to stick or to block contaminants from gas or exhaust from burning engines. Catalyzers get exhausted after some time of working. Why this? Because catalyzers finishes their monolayer adsorbent capacity, so that the adsorbent particulate are totally covered by adsorbate. At this point, the catalyzer stops working. And you may recall that in this case, you may regenerate the catalyzers by simply cooking or heating it. So a way of regenerating catalyzers for treating exhaustion gases from combustion engines is that of heating the catalyzers, so that you have a release from the solid matrix onto the gaseous matrix, so that you can then free the adsorbent surface of the catalyzers. Okay. So the free isotherms model, recall these are isothermal models, so a model in which we fix the temperature at some values. The free very general adsorption isotherms are the Redlich-Peterson, the general one, the Freundlich, in which you have a continuously but slowly growing quantity of adsorbate onto the adsorbent surface. So this is a multi-layer adsorption processes. So once the first layer, the first layer of the surface of the adsorbent particle is covered, then you will have more particles that will be stick to subsequent layers. While if you have a single layer adsorption process, you will employ the Langmuir isotherms, but reaches a plateau dynamic steady state in which you have finished the capacity of adsorption of the particulate. Now let's give a look to the very general model that is called the equilibrium partition or the partition coefficient model. All the models that we have seen up to now maybe simply recasted or rethinked by setting with two parameters delta and beta equal to 0. So we are in the case in which we have equal parameters beta and delta, and in particular these parameters are set to 0. So we are in the case of a Freundlich isotherm. In the case of a Freundlich isotherm, we may generalize this model. So the model of Freundlich, that is a slowly growing adsorption model, by introducing the partition coefficient description. So we set delta and beta equal to 0, and then you rewrite the adsorption model by saying that the concentration in the solid phase QS is equal to the partition coefficient K times the concentration in the liquid phase. Then we are left with the problem of finding some practical definition or expressions for the partition coefficient K. From experimental observations, we have several ways of introducing this definition. First of all, we may realize that at least for non-ionic organic chemicals, we may rewrite the partition coefficient as a function of FOC, that is the weight of a fraction of total carbon in the solid matter, times KOC. KOC is the organic carbon partition coefficient. What we are writing here, we are writing that the concentration in the solid phase is proportional to the concentration in the liquid phase. And the constant of proportionality, K, depends on the quantity of organic carbon that is found in the solid matter, so the quantity of organic carbon in the adsorbent, times a parameter KOC, that is the organic carbon partition coefficient, that describe the friendliness of the contaminant with carbon. You know, as environmental engineers, that organic carbon is always an important parameter to be taken into account when you want to describe the fate of contaminants, because most of the contaminants of interest for the environmental engineer have a more or less large affinity to organic carbon, meaning that the contaminant of interest for the environmental engineer are more or less prone to bind to organic carbon. So what we are saying here is that the concentration in the solid phase is proportional to the concentration in the liquid phase CS times a partition coefficient that depends on the quantity of organic carbon in the organic matter, that is FOC, the fraction of total carbon in the solid matter, not organic but the solid matter, multiply the affinity of organic carbon, the affinity to organic carbon of the particular substance or contaminant we are looking at. So please note that here we are introducing two parameters, FOC and KOC, describing characteristics both of the adsorbent and of the adsorbate. The characteristics of the adsorbent are described by the FOC, so how much carbon is present in the adsorbent, in the solid that is adsorbing, and the characteristic of the adsorbate is the KOC, so the easiness of the contaminant to stick to organic carbon. So we are left with the problem of determining these two parameters in order to calculate or to determine the partition coefficient K. For the FOC, this is quite easy because it is a matter of making, for example, analysis on the organic carbon content of the suspended solids. And you can do this by several methodologies, several lab methodologies, like, for example, ionic adsorption or simple chemical analysis. While for determining KOC, this is a little bit more complicated because it is a matter of identifying a partition coefficient for a dynamic process. We know from experimental observation that there is, from literature or empirical relationships, that there is a linear relationship linking the KOC, so the organic carbon partition coefficient, to the KOV. KOV is the octanol water partition coefficient. The constant of proportionality is exactly given by 6.17 times 10 to the minus 7. So we may say from literature and empirical observation that the KOC, so the affinity of this adsorbate to the adsorbent is proportional to its affinity to octanols. So the KOV. What is the KOV? The KOV is the contaminant's octanol water partition coefficient. Is measured in milligram per cubic meter of octanol divided by milligrams per cubic meter of water. So this parameter KOV describes the affinity of a contaminant to water or to octanols. So it describes the easiness or the ability to be dissolved of a contaminant. And this is a characteristic of a contaminant, while the FOC is a characteristic of the adsorbent, so of the solid matter that is absorbing the contaminant from the dissolved phase onto the solid phase. I know you have already seen all these types of models from your ecotoxicological classes, but I like to recall it here in order to cast it or recast it in the framework of modeling of ecological processes. In particular, this relationship that links KOC onto the KOV may be recasted in this way by this model. So we may say that the KOC is equal to a constant alpha times the KOV elevated to a constant beta. So this is a model that links KOV, that is a characteristics of the adsorbate, so the contaminant, to the KOC, that is again a characteristic of the contaminant. If you take a log of this relationship, you obtain a linear relationship between the log KOC and the log KOV. Why we like to employ linear relationships? Because it is much easier to, especially empirically or experimentally, to evaluate the coefficients of these linear relationships. What is the octanol water partition coefficient, the KOV? It is a coefficient describing the ratio of the solubility of a compound in octanol, that is a non-polar solvent, to its solubility in water, that I recall you is a highly polar solvent. The higher the KOV, the more non-polar the compound is. This means that the higher the KOV, the more the compound will be found into non-polar solvents or non-polar matrices. This means that the higher the KOV, the more non-polar the compound is. So you may employ a log KOV as a relative indicator of the tendency of an organic compound to adsorb to soil. Log KOV values are generally inversely related to aqueous solubility and directly proportional to the molecular weight. So you see immediately that there is a relation of proportionality between the KOV and the molecular weight. So again, KOV is a characteristical parameter of a substance that is related to a chemical characteristic of a substance that is the molecular weight, but describes the tendency of a substance to be dissolved in water or to stick on a solid phase. Particular, we may describe relationships between the solubility, or if you want, the fractions, the solid and the liquid fraction of a substance. So you may employ this variable Qs of the concentration in the solid phase divided by the concentration in the liquid phase. So we call this quantity the polar fraction of a substance, Fp, and this polar fraction may be plotted against log KOV, and you may find that for different substances you have a relationship that is kind of a sigmoidal curve, in which strong absorbers, if the substance is put in contact with strong absorbers, you will find much of the substance of the particulate, while if the substance is put in contact with weak absorbers, you will find typically the substance in the suspended solid, so in the dissolved phase. So a different concentration of the solid, of the suspended solid, different concentration of the suspended solid, 50 to 10 to 5 to 1 milligram per liter. So these are how much suspended solid is present in the water column. Depending on the KOV, so depending on the characteristics of the substance, you may find your substance more in the particulate or more in the dissolved phase. More in the particulate or more in the dissolved phase, depending on the characteristics of the adsorbent. So again, with graphs, puts together the characteristics of adsorbent, strong sorbers to weak sorbers, together with the characteristics of the contaminant in terms of KOV. We may plot different values of the different contaminants. These are again Box and Whistler's plots. For example, for pesticides, you have these values, let's say log KOV values between 2 and 4. While, for example, for ethers, the median value of log KOV for ethers is much lower than for pesticides. What does this mean? This means that you may find more likely ethers in the dissolved phase than in the particulate. you may more likely find pesticides on the particulate phase instead than in the dissolved. Is it clear? So this is a tentative of describing where I expecting to find the contaminant in terms of dissolved phase or particulate. I will more likely find the contaminant in the dissolved phase if its log KOV is low, and if we are in condition of making interacting the contaminant with a weak sorber, while I will most likely find the substance, the contaminant, in the particulate or solid phase, the more the adsorber is strong, so for stronger adsorber, and the larger the KOVs of the particular contaminant. Of course, these curves describing the relationship between the fraction of the particulate over the fraction of the liquid dissolved. So the FP, this relationship between the FP and the KOV, log KOV, depends on the quantity of suspended solid. So the larger the quantity of suspended solids, so the more quicker you will find the contaminant onto the solid phase. Okay, these are plots that are very useful for environmental engineers in order to describe or to have a quick forecast on when you will be likely to find substances. For example, this is an indication that explains why for pesticides you shall describe the dynamic of suspended solids, because you will mostly find pesticides on the particulate phase, because pesticides have a large value of the KOV, and in particular, if the particulate that is interacting with these pesticides, like for example, it is a strong sorber, like for example clay, so pesticides in clay will mostly be found in the solid phase. Why, for example, phenols in sand will be mostly found dissolved in the liquid phase. So you understand that this type of graphs are very useful because gives you a first suggestion on which are the processes what you should focus on in order to describe the exchanges between the various phases. In particular, I recall you that we are concentrating here on the biosphere. So we may employ all these set of models in order to describe more in detail the interaction between the hydrosphere and biosphere. I recall you that we have started this lecture by introducing the model describing interaction between the hydrosphere and the lithosphere, that is absorption. Now we shall describe, with all the discussion that we have made up to here, we shall describe interaction between the hydrosphere and the biosphere. So we shall describe how are the transfers, or we shall introduce a model that describes the transfers from the liquid phase onto the biotic phase. So this is the case in which, for example, an animal or an organism or a plant is absorbing a contaminant by absorbing the water that makes up his water environment. In particular, the general model we employ here is called the bioconcentration factor model. So we may write that the bioconcentration factor is equal to the concentration in the biota divided by the concentration in water. I recall you that we had already seen some allometric relationships describing, for example, the bioconcentration factor for some toxicants when we were discussing calibration. So we introduce this model by saying that the bioconcentration factor may be expressed as the ratio between concentration in the biota divided by the concentration in water. Concentration in the biota may be expressed as a function of the concentration of the lipophilic organic compound in the fat tissue. So what we are writing here is that the concentration in the biota is equal to the lipid fraction of the biota times the concentration in the lipid. So this is nothing special, nothing particular here. We are simply recognizing that most of the substances the environmental engineer is focusing on when dealing with ecotoxicological problems may be found in the lipid part, on the lipidic part of the biomass or the biota. So we write that the concentration in the biota is equal to the concentration in the lipid times the fraction of the lipid in the biota. So this is a number describing how much lipid there is in the biota. And this is the concentration you may expect to find the lipid phase. So you write that the concentration in the biota is equal to the concentration in the lipid times the fraction of the lipids, or the lipid fraction. You may wonder if this is true for all substances. Of course, the answer is no, but the answer is meaning that at least for most of the substances of interest for ecotoxicological issues, you will have that these substances are lipophilic substances. So it is reasonable to write that the concentration in the biota somehow is proportional to the concentration in the lipid. And so you may write that the concentration in the biota is equal to the concentration in the lipid times the concentration times the lipid fraction of the biomass. Then you may recall that the KOV, so the octanol water partition coefficient, may be expressed as a fraction between the concentration in the lipid phase and the concentration in water, because the KOV exactly describe the lipophilicity of a substance. I recall you that the KOV is a characteristic of the adsorbate, while the lipid fraction is a characteristic of the adsorbent. In this case, we're not talking about absorption here, but we are talking of bioconcentration. But the concepts are the same. So this F lipid is characteristics of a living organism, but is bioconcentrating the contaminant, while KOV is a characteristic of the contaminant itself. If you put all this together, you may say so that the bioconcentration factor is equal to these quantities. You simplify the concentration in the lipid that is appearing here and here, and then you rest that the factor, bioconcentration factor, may be expressed as a linear function of the KOV times the fraction of lipid. You may generalize this model by writing that log in BCF, so the log of bioconcentration factor is equal to the log of the lipid fraction plus B times the log of KOV. So this model is obtained by putting a log-log relationship to this exponential model. So the bioaccumulation factor describes the uptake from water of plants and animals. So we are talking about bioaccumulation as we have defined it in the beginning of this lecture. So bioaccumulation is describing the ratio between concentration in the organisms and the concentration in water by employing this linear relationship. We may find, by employing this model, we may find a relationship that links the bioconcentration factor to the characteristics of the organism that is bioconcentrating, so the quantity of lipid that is present in its tissues, and the characteristic of the contaminant as expressed by the KOV. A similar discussion may be carried in order to build a model that describes bioconcentration from the lithosphere to the biosphere, for example, soil and sediments. So here we are trying to describe the process of bioconcentration of contaminants into biota from contaminants that have been may be found onto a lithosphere, onto the solid phase. So again, we write that bioconcentration factor in this case is equal to the concentration in biota divided by the concentration in the solid phase. We divide and multiply for a concentration in water, and by employing the model that we have just introducing here, that is the bioconcentration in water, we may rewrite that for the lithosphere biosphere interaction, bioconcentration factor in the biosphere is equal to bioconcentration factor in water divided by KD. And KD is a partition coefficient that describes the affinity of solid substance, the affinity of the contaminant to a solid substance. So we may express KD as a constant x times the fraction of organic carbon times the KOV of a particular contaminant. So we are rewriting the bioconcentration factor in the solid as a function of the bioconcentration factor in water. And you know that the bioconcentration factor in water depends on the KOV. And we are now introducing a new model for the partition between liquid and solid. And we make a dependence, the partition between liquid and solid onto the fraction of organic carbon and onto the KOV of the contaminant. Then if we put all these together, we obtain that the bioconcentration factor in soil, the bioconcentration factor in the biota from solids. So here we are talking about bioconcentration factor of biota from liquids. Here we are talking about bioconcentration factors of biota from solids. By putting all these together, we obtain this relationship that says that the bioconcentration factor in the biota, starting from concentration of contaminants in the solids, is equal to 1.01 times the lipid fraction of the biota times the organic carbon fraction of the solid. So here you have characteristics of the biota. Here you have characteristics of the solid onto which the contaminant sticks. And here you have the characteristics of the contaminant, given that this power is 0.09, almost zero. So there is a very deep dependence, very weak dependence on the KOV. The model that describes the bioconcentration factor, for biota interacting with the lithosphere is simply 1.01 or 1 times the ratio between the lipid fraction and the organic carbon content of the solid. So you see here we are putting together quite a complex chain of exchange processes in which we are describing the effect of a contaminant substance that is being sticked onto the solid by adsorption processes, so transfer from the liquid onto the solid, and then we are describing the fact that these solids are entering into the trophic chain of larger organisms through foods. So we are describing the effect of biomagnification, so the effect of transfer of contaminants from liquid to solids, from solids to the biota. So this is the interaction between lithosphere and biosphere, and the interaction between lithosphere and biosphere, it is very simply described by the ratio between the lipid fraction and the organic carbon content of the solid, and the dependence on the QOV, that is a characteristics of a toxic substance, is quite low. What does this tells us? This tells us that essentially having a contaminant dissolved in water or having a contaminant adsorbed onto solid, if you have an organism that is living in a water environment, so it's assuming water, and as well it is assuming food or solids, then the characteristics of the contaminants are less relevant than the characteristics of the solids in terms of organic carbon fraction and the characteristics of the biota in terms of the lipid fraction. Okay, I will stop here for today. Next week we will start discussing balance, transport, and chemical reaction models, that are the next step of the physical processes. Do you have any question? Is it clear what I've told you about ecotoxicological processes? If not, if you don't have any question, I stay in the class for 10 minutes and then I quit and I go to have a coffee. Ciao, scusami, sono in classe, dimmi. Sto facendo lezione. La faccia sono a un tegretol, riesco a controllarlo con un tegretol, 2 mezzi, un mezzo la mattina, un mezzo la sera.
All'università o a casa?
Sono a casa, sto facendo lezione in Zoom.
Ah, vabbè. Volevo dirti, Luca, indipendentemente da tutto quanto, ci fa bene incontrarci, quindi vieni giù il più presto possibile. Pronto, mi senti?